how many configurations do we increase, or by what factor do we increase when we, say, melt a glass, kind of an ice cube, like a 1 liter ice cube or something. So what we have, again, is the change in entropy is equal to the change in heat input at a particular temperature, and this is related to the number of configurations with the natural log. So we have the S is equal to K times the natural log of the number of configurations. So this allows us to link things like temperature and heat into number of configurations. So in this case, say I want to melt 1 kilogram of ice and ask how many configuration changes that is. Well, how much energy does that take? Well, it takes 334 kilojoules, so times 10 to the 3 joules, to melt 1 kilogram. So that's going to be the amount that we're going to have, and this is at 273 Kelvin. So this gives us, change in entropy is 334 times 10 to the 3 joules over 273 Kelvin, or about 1,200 joules per Kelvin. Relating this to the change in the number of configurations, we get 1,200 joules per Kelvin is equal to K, which is Boltzmann's constant, 1.4 times 10 to the negative 23 joules per Kelvin, times the log of the ratio of the final to the initial number of configurations. Then this ratio then, final to the initial, the log of that, becomes about 8.7 times 10 to the 25. I can divide by 2.3 to get the base 10, and then what I get is essentially the ratio of the number of configurations after melting compared to what it was before melting is 10 to about 3.4 times 10 to the 25. So it's again an extremely large number when we talk about configurations. That's why we usually talk in terms of log of those configurations. It makes it much more handleable. But but if you think in terms of all these molecules bouncing around, dumping heat in, you get various changes that happen in terms of how much that energy kind of evens out. We get increases in the number of configurations.